When we look at the night sky, we see countless stars. Each one is a sun for some distant planet. But among all these shining points, one star occupies a very special place in our lives. It dominates our sky. It gives us light, warmth, and strength for all living things. It is so large and so bright that during the day it eclipses all other stars. And yet, strangely enough, this star is the most ordinary. A yellow dwarf of average age and average size, of which there are tens of billions in our galaxy. This is our sun. For millennia, generations of people have gazed upon it and tried to understand what it is. The ancient Egyptians worshipped it as the god Ra. The Greeks saw it as the chariot of Helios, passing daily across the sky. The Aztecs made bloody sacrifices to it so that it would not stop. All these attempts to explain the sun were, of course, legendary. But behind each of them lay the same feeling of awe before that which man did not understand. Today, we understand much more, and in recent decades, thanks to spacecraft and ground-based telescopes, we have peered deeper into our star than ever before. We have seen it layer by layer, like a sliced piece of fruit, revealing what is hidden from the naked eye. Today, I invite you on a journey. We will travel from the outer reaches of the solar atmosphere down to the very surface and see the star as scientists see it. Before we go, it's important to say something striking. The light you see when you step outside in the morning and squint against the bright sun is very old light. Light is the fastest thing in the universe, but even it takes about 8 minutes and 20 seconds to travel from the sun to Earth. So when you look at the sun, you're not seeing its present, but its past. If the sun suddenly disappeared right now, you'd only know it after more than 8 minutes. But that's not all. That beam of light that hit your eye and made you squint didn't just travel from the sun's surface to your retina. It was first born in the very center of the star through nuclear fission, and before it could escape, it had to pass through layers of extremely dense matter, constantly colliding and being re-emitted billions of times. This process takes tens of thousands of years. The light you see from the sun today was born in its depths, when mammoths might still have roamed the Earth. This light is between 10 and 170,000 years old. Think about that the next time you feel the warmth of the sun's rays on your skin. These rays have been traveling to you longer than modern human civilization has existed. So, let's begin our journey. We'll move from the outside in, as if peeling a fruit. And the first layer we encounter will be the sun's corona, the outer part of its atmosphere. The corona extends for millions of kilometers beyond the star's visible surface, but in ordinary light it's nearly invisible, outshone by the enormous glow of the main disk. The corona can only be seen with the naked eye during the rarest of moments, during a total solar eclipse. When the moon briefly aligns perfectly between the Earth and the sun, it blocks the bright central disk, and the ghostly glow of the corona appears around it. It's one of the most stunning spectacles that can be observed from the surface of our planet. Many people plan trips to the other side of the world specifically to catch a few minutes of the total eclipse. But even the best eclipse won't reveal the corona in the detail that modern instruments can. Since 2010, NASA's Solar Dynamics Observatory, or SDO for short, has been operating in space. This spacecraft is specifically designed to continuously photograph the sun in a wide range of light bands, from visible to ultraviolet and X-ray. Every 12 seconds, it transmits new images of our star to Earth in 10 different bands simultaneously. In a single day, this spacecraft sends back about 1.5 terabytes of data, more than an entire library of high-definition films. Many of the most stunning images of the sun you've seen online or in popular science programs were taken by this spacecraft. And now, looking at the corona through this spacecraft's ultraviolet eye, we see what corresponds to a temperature of about 1,000,000 degrees. This, in itself, is a mystery, to which we will return. But let's dive a little deeper. Just below the upper corona are even hotter regions, 20 million degrees or more. This is where phenomena called solar flares occur. These are enormous explosions during which the sun ejects an unimaginable amount of light and radiation into space. A single large flare unleashes enough energy to equal the energy consumed by humanity over millions of years. Flares are caused by the sun's magnetic fields. The star consists of plasma, a special hot medium in which electrons are torn from their atomic nuclei. The plasma conducts electricity, and its movement creates complex, intertwined magnetic fields. Sometimes these fields converge at a single point, twisting like a rubber band, and at some point, what's called magnetic reconnection occurs. The field lines abruptly shift their positions, and the accumulated energy is released in a single, powerful burst. If such a flare is directed toward Earth, the consequences can be quite serious. Charged particles, accelerated by the explosion to enormous speeds, slam into our magnetic shielding. Fortunately, Earth has a magnetic field. It deflects most of the impact. But even through this shielding, large flares can disable satellites, disrupt power grids, and interfere with radio communications. The infamous Carrington event of 1859, the most powerful flare in recorded history, ignited telegraph lines around the world and caused the aurora borealis to blaze in the skies over Cuba and Hawaii. Telegraph operators in the US and Europe reported sparks shooting straight from their machines, paper igniting from interference in the wires, and some lines continuing to function despite their power sources being completely disconnected. They were powered by pure solar current. If such a flare were to occur today, the damage to modern electronics would be catastrophic. According to various estimates, restoring the networks would take years and cost the global economy trillions of dollars. The closest we came to a repeat of the Carrington event was in July 2012, when a powerful ejecta literally passed by Earth. It crossed its path, but at a point where our planet wasn't present at the time. If the same ejecta had occurred a week earlier, you might be reading this by candlelight. Besides solar flares, there are other bright phenomena on the Sun. For example, coronal holes. In ultraviolet images, they appear as dark spots because the plasma in these areas is cooler and less dense than in the surrounding regions. But it's not just a matter of temperature. Coronal holes are structured fundamentally differently. In normal regions, magnetic field lines form closed loops, extending out from the surface and then returning. In coronal holes, the magnetic field lines are open. They extend straight into outer space. Through these holes, charged particles can escape the Sun unimpeded, forming the so-called solar wind. And it is these streams of particles, reaching Earth and crashing into its magnetic field, that give rise to the aurora borealis, the incredible iridescent glow in the skies of the northern and southern regions of the planet. Every time you see images of the northern lights over Norway or Alaska, you know visitors have come to visit us from a coronal hole on the Sun. Let's move on. Enormous structures called solar prominences, or more generally, solar filaments, hang over the surface of the Sun. These are enormous loops of plasma that rise from the surface and are held in the atmosphere by magnetic forces. The size of these loops is absolutely staggering. The Earth appears as a tiny dot next to a typical prominence. They can stretch hundreds of thousands of kilometers into space. What's most astonishing is that these structures form in literally a day and can exist in a stable state in the corona for several months before collapsing. If you watch a time-lapse video of a large prominence forming, you can see how it seems to writhe like a huge, glowing snake. Each movement, which appears to last only a second in the video, takes minutes or hours in real time. But when you consider that we're talking about structures the size of tens of Earths, it becomes clear just how monstrously fast this material moves under the influence of magnetic forces. And, as strange as it may sound, it sometimes rains in the solar atmosphere. I'm not kidding. Not all the plasma ejected into the corona escapes into space. Some of it gets trapped in magnetic fields, gradually cools, and, under the influence of gravity, flows back to the surface, like droplets. Scientists call this phenomenon coronal rain. High-resolution images show streams of glowing plasma flowing along enormous arcs of magnetic lines, like water flowing through invisible gutters. It's an incredibly beautiful sight. However, it's best viewed from a distance. The raindrops still have temperatures of millions of degrees. If the magnetic structures holding the plasma can't withstand it and are torn off, what occurs is called a coronal mass ejection. While in the case of rain, the plasma peacefully flows back, here, things are different. The magnetic structure, like a spring stretched to its limit, is suddenly released and hurls billions of tons of plasma into space. These ejections travel at speeds of hundreds and even thousands of kilometers per second. If such an ejection were to strike Earth directly, the consequences could be very serious. The same damage to networks, satellites, and radio communications as with major flares, only on an even greater scale. All these formations, flares, prominences, coronal rain, mass ejections, are observed using different ultraviolet wavelengths. And here's the interesting point. If you look at the same region of the Sun in two different wavelengths, you can see completely different things. For example, in the wavelength range corresponding to a temperature of 600,000 degrees, we see a quiet corona with its closed loops. But in the wavelength range corresponding to 2 million degrees, the same region looks completely different. The hottest, most active regions are visible there. It's like looking at the same house at night with and without a thermal imager. The same building, but different things appear in the light. This is why modern solar science relies on simultaneous observations in several wavelengths. What appears to be a single phenomenon is often actually a complex chain of interconnected events occurring at different temperature and density levels. Before we even reach the visible surface of the Sun, we must cross a very thin but crucial layer. It's called the transition zone. It's only about 100 kilometers thick. For a star 1.5 million kilometers across, that's literally the skin of a fruit. But it's here that one of the most mysterious things in all of solar physics occurs. In these 100 kilometers, the temperature jumps sharply from 8,000 degrees to about 500,000. To give you an idea of the magnitude, the scorching lava erupting from the Kilauea volcano in Hawaii has a temperature of about 1,443 degrees. The lower boundary of the transition zone is almost 6 times hotter than this lava, and the upper boundary is more than 346 times hotter. And all this within a gap of 100 kilometers. This is a completely unnatural picture in terms of our everyday experience. When you move away from a fire, it gets colder, but here it's the opposite. The farther you get from the surface of the Sun, the hotter it gets. This is one of the main unsolved mysteries of modern solar science, known as the coronal heating problem. Why is the star's atmosphere hotter than its surface? Scientists have been searching for an answer to this question for decades. I'll share some of their theories in a few seconds. We descend even lower, to the chromosphere. This is the last layer of the atmosphere just before the star's surface. The chromosphere is about 1,700 kilometers thick. In ultraviolet images, it appears as a reddish, uneven layer, and upon closer inspection, amazing formations, spicules, can be discerned within it. These are long, thin streams of plasma that literally shoot up from the Sun's surface into the atmosphere. In photographs, they resemble grass swaying in the wind. Just imagine their size. Each stalk of this grass is almost 10,000 kilometers long. That's longer than the distance from Moscow to Los Angeles. Mount Everest, the highest peak on Earth, would look like a tiny hummock against the backdrop of such a spicule. The speed at which these streams rise reaches 100 kilometers per second. That's approximately 280 times the speed of sound. And they live only 5 to 10 minutes, being born and disappearing, constantly being replaced by new ones. At any given time, about 1 million spicules exist simultaneously in the Sun's atmosphere, a whole forest of thin plasma geysers through which the star breathes. For a long time, the structure of the spicules remained a mystery. Scientists couldn't understand how charged plasma particles could escape the powerful magnetic fields in this zone. The magnetic fields should have held them in place. Then, in 2017, after nearly 10 years of intensive work, an international team of researchers, using data from a space telescope and the Swedish Solar Telescope on the island of La Palma, finally offered an explanation. The key to the solution turned out to be neutral particles. Previously, scientists had based their calculations of solar plasma on the assumption that all matter there was fully charged, that is, composed only of charged particles. This simplified the mathematics. But reality turned out to be more complex. In the relatively cool lower layers of the solar atmosphere, some atoms remain uncharged. They are not affected by magnetic fields. When the researchers added these uncharged particles to their calculations, which took nearly a year on NASA's most powerful computing device, the spicules finally appeared in the recreation, exactly as seen in the real images. It turned out that the uncharged particles give the charged particles a kind of extra buoyancy, allowing them to escape their magnetic confines and rush upward. This was an important discovery, because spicules may play a key role in the very problem of coronal heating. Through them, matter and force are transferred from the lower atmosphere to the corona. If your curiosity tells you that these tiny plasma geysers could be one of the main drivers of the mysteriously hot corona, you're probably on the right track. And now, finally, we've reached the very surface of the Sun, the photosphere. This is the region we see as the star's visible disk, and it's best observed in ordinary visible light. At first glance, the edge of the photosphere appears crisp and sharp, as if the sun had a solid shell. But that's a deception. The sun has no shell, and it's not a solid at all. The sun's interior is so hot that matter cannot exist as a solid, liquid, or gas. It exists only as plasma, the fourth state of matter, consisting of charged particles. Incidentally, plasma makes up about 99.9% of all visible matter in the universe. Stars, interstellar gas, nebulae, all of this is plasma. The solid, liquid, and gaseous states we're accustomed to are cosmic rarity. The thickness of the photosphere is about 400 kilometers. The sad news is that this is the deepest layer of the sun we can directly observe. Our eyes and our instruments can't see deeper than the photosphere. Everything beneath it can only be studied indirectly, through surface vibrations, incoming neutrinos, and theoretical calculations. The famous sunspots can be seen on the surface of the photosphere. In photographs, they appear as dark blobs, and many people think they are some kind of holes or dips in the sun. In reality, they are simply areas where the temperature is slightly lower than the surrounding temperature, around 4,000 degrees instead of the usual 6,000. By terrestrial standards, this is still unimaginably hot, but compared to the surrounding photosphere, these areas appear dark. Sunspots occur where magnetic fields are particularly strong. In these areas, magnetic lines hold the hot plasma rising from within, preventing it from mixing properly, and the surface cools slightly. What's particularly interesting is that if you compare a visible light image of the sun, which shows sunspots, with an ultraviolet image of the same area, which shows flares, a clear connection is revealed. Flares and sunspots occur in the same places. Magnetic activity, manifested as a sunspot on the surface, erupts in a powerful explosion in the upper atmosphere. The connection between these phenomena is fundamental, and it is this connection that helps scientists predict space weather. Incidentally, the frequency and strength of all the phenomena described, spots, flares, mass ejections, do not remain constant. The sun follows a roughly 11-year activity cycle. There are periods of relative calm, when there are almost no spots on the surface, and flares are rare. And there are periods of vigorous activity, when the sun literally boils, and large flares occur almost daily. Now, in the 2020s, we are experiencing the maximum of the 25th solar cycle, that is, the 25th since scientists began counting them. This is why in recent years there have been so many news reports of powerful flares and unusually bright auroras, visible even in mid-latitudes. Another amazing detail of the sun's surface is the solar granules. If you look at the photosphere in very high resolution, for example with the Swedish Solar Telescope, you'll see that it's completely covered in tiny cells with bright centers and dark boundaries. They move, appearing and disappearing like bubbles in a boiling pot. These are the granules, the tops of the boiling cells. Inside each granule, hot plasma rises from deep within the sun to the surface, gives off heat, cools, and flows back down along the dark boundaries of the cells. It's the same process that occurs in a pot of water on a stove, only the dimensions are slightly different. Each granule is about 1,000 kilometers wide, larger than many countries on Earth. The plasma within them moves at speeds of up to 7 kilometers per second, supersonic speed, even by solar standards. Its movement across the sun's surface creates veritable sound waves, veritable booming concerts, audible to instruments as seismic vibrations. Each granule lives for about 20 minutes on average. It's born, exists, and disappears, only to be replaced by a new one. Incidentally, the granularity, sometimes visible in ultra-high-resolution photographs of the sun, is often mistaken for camera noise, but it's not noise at all. These are granules, true seething cells on the surface of our star, each the size of a continent. And here, unfortunately, our journey ends. Beyond that, below the photosphere, into the boiling depths of the star, modern science is not yet capable of peering directly. Much of what happens in the deeper layers remains a guess, based on indirect evidence. But even what we have seen is astonishing. It's also worth mentioning that in recent years, the sun has become even closer to us, not figuratively, but literally. Since 2018, a special NASA spacecraft has been orbiting our star, named after the American scientist Eugene Parker, the man who first predicted the existence of the solar wind back in the 1950s. It's called the Parker Solar Probe. This spacecraft is the boldest space project ever to attempt to get close to the Sun. It dives into the upper layers of the corona to a distance of only about 6 million kilometers from the star's surface, 7 times closer than any other spacecraft has ever come. To withstand the monstrous heat and radiation, engineers developed a special shield made of carbon with a ceramic coating. The shield, approximately 11.5 centimeters thick, heats up to 1,500 degrees Celsius on one side, while the other side, where the instruments are located, remains at room temperature. The speed at which Parker passes the Sun is also incredible, about 700,000 kilometers per hour. It is the fastest man-made object in human history. The spacecraft has already made dozens of close encounters with our star and collected a colossal amount of data. It is thanks to Parker that we have finally been able to see what happens inside the corona, from the inside. And it is precisely its data that is now helping scientists understand the problem of coronal heating. Perhaps in a few years, we will have a definitive answer to the question of why the Sun's atmosphere is hotter than its surface, and this answer will come directly from within. We passed through the blazing corona with its flares, prominences, and ejections. We crossed the unusually hot transition zone. We raced through the chromosphere with its plasma spicules. We found ourselves at the very edge of the visible Sun, the photosphere with its spots and granules. Each of these layers was revealed to us only thanks to modern science's ability to see light beyond what the normal human eye can perceive. Without ultraviolet, X-rays, and thermal rays, this entire scene would be invisible to us. The ancient Egyptians and Greeks saw only a small golden circle in the sky. We see an incredibly complex, moving, seething plasma machine. Perhaps in 100 years, our descendants will laugh at how little we knew at the beginning of the 21st century. Perhaps they will see the Sun in ways we can't even imagine now. They will peer directly into its core, observe how rays of light are born in nuclear transformations, track the path of every plasma particle. And today's images from the Space Observatory will seem as simple to them as the Sun's depictions in cave paintings do to us. But even this is no cause for sadness. It is a cause for admiration. Each generation of people has pushed the boundaries of understanding a little further, and each generation has left questions for the next to solve. How much is still hidden in our star, waiting to be discovered? How many processes are there that we don't even suspect yet? The answer to this question is simple: a lot. And it is precisely this mystery, this inexhaustible knowledge, that is perhaps the most amazing thing about science. Every time we think we understand something, the universe presents us with a new riddle, and our beloved Sun is no exception. It has been shining upon us for 4.5 billion years, and it will continue to shine for about the same amount more. We have plenty of time ahead of us to gradually unravel all its secrets. The main thing is to keep watching.